we'll think about another representation of that equation using just analog of Newton's second law for rotational motion. So that analog tells us that it would be product of torque, it would be product of moment of inertia by angular acceleration. So we can write I, moment of inertia of cylinder, by alpha z. Now, for objects of certain symmetrical shapes, there are tables where you can find the moments of inertia of all those, like spheres, cylinders, rods. If object is not symmetrical, then it is more complicated to compute, but for symmetrical, it is computed. So we can find in that table that moment of inertia of cylinder would be 1/2 mr squared. No, and that is, of course, for a situation when axis of rotation, when the cylinder rotates about its symmetrical axis, 1/2 mr squared. So that expression we can substitute over here, and we'll get that sum of all torques then, which is RT, again, which is 1/2 mr squared alpha z. Here also you'll notice that what it is AY. AY, it would be a tangential component of acceleration. Tangential component of acceleration related to angular acceleration, object rotates with angular acceleration alpha z, in the way that, let me start from that, AY, which is A tangential part, that is R by alpha z. From this alpha z, it would be A y divided over R, and we can substitute that expression here. So that would be 1/2 mr squared AY over R. When R goes away, thus we have a system of two equations. That is one, and that is another one. And we have two unknowns, so you can imagine that we can solve those equations and find our unknowns. Probably let me do it on that side. Just let me write down those equations what we have. Minus T equals MAY. And another one, RT, would be equal 1/2 mr AY. So solving those nodes, for example, we can add up, so that and that cancels out, that if we add those two equations, T will go away, and we can find that then AY would be equal G divided over 1 plus 1/2 m over m. You can check yourself. And t can be resolved and found it would be mg divided 1 plus 2m divided over m. That would be our intention in the table. So as you saw, we applied translational dynamics to the block and rotational dynamics to the cylinder because they performed a different kind of motion. Block was moving in linear manner and the cylinder was rotating. So that's why again we use two free body diagrams, wrote two equations accordingly, two Newton equations, one for linear motion, one for rotational motion. Okay, so next what we will do, we'll do another problem. Let me pull it from here. So the problem would involve rolling without sleeping. Example of wheel could be sleeping, could go without sleeping. Object, particularly wheel, will take a wheel and cylinder. It will race down the inclined plane. And we'll find the acceleration of that rolling sphere. And about angular momentum, I don't know, probably we'll discuss with you in next class. Okay, you can see the problem. This is a little larger proportion. So in this problem, you see we have inclined plane with angle, part of incline is shown, angle theta of incline. We know already very well, we did a lot of decomposition of forces acting on the object on inclined plane. Angle of incline would be that particular angle theta can be proven and was proven many times. So we have two objects, one solid sphere and another hollow sphere. I told you wheel, but actually it is hollow sphere. No, you can try for rolling down a wheel or disc or anything, because it is generally true. So we want, so that's what is known, and we want to know conditions on coefficient of friction for that object. Let's start from solid sphere, for example, going downward without slipping, no slipping. So you can imagine if there would be no friction, it would just slide downward, but it rotates when it goes down because there is no slipping. So what would be coefficient, minimum value of coefficient, which produces that condition for such motion, no slipping. No, and that is for sphere, and that is for hollow sphere. The question here would it be coefficient of static friction or coefficient of kinetic friction? Which one? Here should be, there is a typo, K. Yeah. So, as in previous case, we will need to do free body diagram. For example, for that sphere, and then what forces would be acting on that sphere. So, we'll start from weight, mg. We can decompose on component along inclined plane and perpendicular to inclined plane. So that part, mg sine theta, would be responsible for pulling object down the inclined plane. Perpendicular would be pressing object towards the inclined plane, so it would be responsible for any frictions involved. And because object participate in two types of motion, and linear motion, it goes along the inclined plane, and rotational motion too, at the same time. So we will write Newton's second law first for the linear motion. We'll address center of mass, because that would reflect best motion of the object. Yeah, so sum of all forces acting on the sphere would be expressed through product mass of the sphere multiplied by acceleration of the sphere, which will take just acceleration of center of mass. Center of mass acts and moves like the whole mass of the object would be concentrated at that particular point. That's why the importance of center of mass, because we can describe motion of complicated object like motion of point-like particle with mass equals to all mass of the object, which is located at center of mass of that object. So that's why we write here acceleration of center of mass. Another important part here would be y component of that force. So for Fy, we can write that it would be mass by Ay. So that would be, from that we can determine a force pressing to incline. So normal force, no, obviously acceleration Ay would be equal 0. So Ay would be equal 0. So from this we get the normal force mg by cosine theta. Now, force of friction. Force of friction would be expressed like coefficient of friction by mg by cosine theta. Now next we can analyze what's going on in x direction. So that part describes some of forces acting in x direction. So it would be component with sine theta and minus force of friction acting. So that would be MA, should be x, but I need z because it would be just 1A present in the problem. So thus we get equation from this one by canceling masses in that equation. So that would be our first equation, which we have written. Next we will write Newton's second law for rotational motion. Non-rotational motion of center of mass. So we will write that sum of all torques acting on that sphere would be equal to angular acceleration multiplied by rotational inertia or moment of inertia. So we would need to compute that torque. Non-torque would be force of friction multiplied by lever arc, which will be arc in this case, radius of the sphere. So torque of force of friction, we can say, that's why we supply this F, would be mu S mg by cosine theta. So mu S by mg cosine theta, that is friction force, our friction force, and multiplied by radius. So that would be our net torque. No, actually, it would be a torque of just 1 force F. Now, we remember that we can always look up moment of inertia of sphere in table, so that will be 2/5 mr squared. And thus, we can write that tau F like 2/5 mr squared. So now, that condition of no slipping, what does it mean? It means that we can write a relationship between angular acceleration and linear acceleration in this form, what we normally use. Because if it would be slipping, then that relationship won't be true. They would be equal they would not be related with that equation. So thus, we can write for torque of force of friction acting on the sphere 2/5 mr squared A over R. And here again we cancel out R, 1R goes away. So we can write our second equation. So that equation comes from we wrote before that the torque, it is mu S mg by cosine theta R. It's just definition of torque, R by A, right? So that's what comes. Left part, right part comes from Newton's second law for rotational motion. That would be I by angular acceleration. So we can say that that is definition of torque itself, R by F. On the right side, Newton's second law for rotational motion, which is I by angular acceleration alpha. So thus we get second equation from analysis of rotational motion of that sphere. You see here that system, equation 1, equation 2, and we can solve it and find A from this. Another unknown here would be mu S, which we could find. but we are just interested in set A. So we see some steps that, for example, we can divide one equation over another and extract that way our A, find our A. For hollows here, we do similar steps, but for moment of inertia of hollows here, formula not 2/5 mr squared, but 2/3 mr squared, because hollows here of the same mass has larger moment of inertia, because more mass would be located more distant from axis of rotation. And likewise, we can compute acceleration of the sphere, and we also can find the coefficient of friction. So that problem is downloaded, so we look at it at home also, and if any questions, of course, you can ask as always.